Yeah, so I'm a PhD candidate at Johns Hopkins University. I want to give a big thank you and shout out to my advisors, Yinzhi and Matt, who are great supports in this work as well as in general. So yeah, in this talk, I want to talk about secure protocols, including ones we heard about even earlier today, such as prime match. Largely, this is in the space of MPC, but this actually also covers things like FHE and zero-knowledge proofs, and we'll get into exactly how shortly. But in general, the use of secure protocols is increasing. Things are becoming massively more practical in terms of performance and the size and complexity of programs that can be run within secure protocols. Everything from way back in the day, like for example, the sugar beets MPC, to more complex and recent approaches such as the Boston Women Workforce Council MPC, measuring wage inequality in Boston, to things like matching stock inventories or buy and sell orders. So in general, these secure protocols are rigorously proven secure, with this caveat that is sort of well understood in the cryptographic community, that this is modulo any leakage inherent to the underlying functionality. And usually we sort of just say like, okay, well, we're aware of this, how bad is it? Well, we're maybe not sure, but if it seems too bad, maybe just don't run the protocol. And so in this work, we really wanted to dig into this question, like truly for protocols that we care about, how bad is the leakage, to the point that we can sort of systematize and understand whether we want to run certain protocols with our valuable customer data or patient data or whatever it might be. So I'll motivate this, or at least explain this first with a sort of a toy example of the Yao Millionaires MPC, which is this very simple protocol which compares two salaries, presumably of a few millionaires who want to compare who has more money without actually giving away their wealth number. So this is a very simple predicate function, just comparison MPC to run this protocol securely. Now you can pretty naturally understand that this immediately leaks a bit of information about your partner's input, whether it's larger or greater or larger than yours. So if you were to say pick a salary right in the middle of the range, you could learn that high order bit. And so what we sort of hinted at there is that there is sort of an optimal strategy here. Guessing right in the middle of that range actually tells you the most about the other person's input, whether it's greater or lower, and divides the possible space in half. And that's a core concept. Then the easiest way to show that this leaks a bit of information is that if you were maybe to run this protocol log n times, you'd be able to completely identify the other party's input. So A less than B, not quite a general function. I mean, this is an instance of a function, but when we want to look at functions that are far more complex, far broader than simple examples, can we do this in practice, and can we do better than sort of saying, well, maybe there's some leakage. Let's hope for the best. And the answer is absolutely yes, as we'll get into in this talk. In general, doing these analyses by hand could be, maybe not worth the time. It can be, require certain expertise that maybe isn't held by the people who just want to decide whether they want to engage in using a protocol. In the example of the BWWC, companies were opting in to provide salary data. Maybe they don't necessarily have the time or expertise to analyze the functionality and say, does this leak? Does this or does this not leak, regardless of the strength of the encryption itself? So as mentioned, this can also be similarly applied to functions which are evaluated within an FHE if the final result is decrypted and shared, or statements proven in zero knowledge. The statement itself, even if the zero knowledge protocol is perfectly secure, naturally leaks some information, the truthiness of the statement itself. So what we wanted to do is, given only a description of the functionality, automatically estimate leakage. So try to use a tool to systematically evaluate leakage, and then even go a little bit further and automatically generate optimal inputs, or at least nearly optimal inputs to the protocol that could be used to formulate sort of a leakage-based attack. And an important note here is we're not breaking any crypto. We're not invalidating any security proofs of these secure protocols. We're in fact just exploiting the functionalities that they've chosen to encapsulate. So the overall approach, kind of at 10,000 feet, And the kind of core idea of this work was to capture the functionality as a Boolean circuit, and then use a tool from the satisfiability community called model counting to model leakage as the possible solution space for the, say, honest party's input. And then a difference in the size of that solution space implicates a certain amount of information we've gained, say, after a single execution of the protocol. And then the key idea here, which we draw from, or which was made possible by work from Fremont et al. Recently, or relatively recently, was that we can actually take these model counting tools and apply them within a SAT solver as constraints themselves, and use these as an optimization problem to actually drive up or down leakage in a particular example case. So we have some functionality which has some honest parties inputs and adversarial inputs, and we want to consider things like the number of possible solutions for an unknown honest input given one particular adversary input or another. Okay, so I mentioned model counting. In sort of delving a little bit into how this looks. What we want to do is we want to eliminate as many candidates for the honest party's input as we can each time we analyze a functionality. So sort of you can imagine this as a solution space which we are dividing into some unknown but existent subsets. Maybe we have some true honest input M star there, and then potentially be able to eliminate a certain number of candidates which are not consistent with the constraint system. And then in the example case that we're able to, say, run the protocol multiple times, we can even generate sort of a full attack here to go all the way down. In some cases, even just one iteration is enough to fully leak a private input. In many other cases, you can simply learn a certain number of bits, a certain amount of entropy, or reduce the entropy of the hidden input. And in general, if you're allowed to, say, run the protocol many times, maybe it's in a client server model, et cetera, you could launch a full attack and fully uncover an honest input. So we build heavily off of our previous work, Delphinium, which we actually used a similar technique to analyze Chosen-Ciphertext attacks, which generally leverage padding oracles and more generally format oracle attacks to decrypt ciphertexts. Again, without attacking the cryptography itself, but rather functions that are used, for example, padding or other format checks on the plain text. Notably, this depends on predicate functions, which can say whether a message is valid or invalid. And there's also a further restriction that they need to be well-formed in a particular way that I don't quite have time to get into. But if we want to look at general functions with, say, n-bit outputs rather than 1-bit output, and also expand beyond the sort of requirement of well-formedness that we established in that previous work, we have to solve a few challenges. And the core idea of this was a navigation of this massively larger outcome space, right? N-bit outputs, 2 to the n possible outcomes within that, and then actually the power set of that number of possible subsets of the outcome space. So we naturally can't explore that exhaustively. We'll just be immediately dead in the water. So what we developed was a heuristic which explores the space much more efficiently, which is not necessarily globally optimal, but it does work in practice to greedily select a subset of outcomes which can be simultaneously constrained over and where we can launch our leakage maximization constraint problem. So threw a lot at you there. The details of this are all found in the paper. Unfortunately, can't get too far into it because we'd just be talking about SAT theory for a while. But hopefully I can demonstrate to you at least that we can identify in even just a single execution approximate lower bounded leakage for many functionalities. We can go through exactly what all of these evaluation cases are in the full work, but everything from toy examples like Yahoo Millionaires to dual execution MPC, various MPCs derived from the Women's Workforce Council MPC work at Boston University, the Sugar Beets auction functionality itself, and as well as a few others. So in just a single iteration, just looking at the functionality, our approach can estimate leakage. And then, as I mentioned, if we allow the tool to continue, for example, in the setting where we're able to rerun a protocol multiple times, you can see that for example, for a 64-bit Yao millionaires problem, you can very close to get those 1-bit per query in practice. And now there is an inherent approximation of an NP-hard problem in each iteration of this attack. And so there are, naturally cases where it does not quite make that 1-bit per 1-bit per iteration. But we find that, as this scales up, the approximations end up being, reasonably good, right? It's this wonderful example where we're looking at this optimization problem over an NP-hard problem. And if we consider that in the worst case, then we're in a situation where it's like we simply can never approach solving this. But the thing that we exploit in this work is that NP, or that worst case complexity is not average case complexity. We chose some relatively smaller examples to evaluate for this so that we could run them many, many times in repetition to get good ranges, et cetera, and really explore the variance. But in general, minutes of tens of seconds to minutes of computation for these examples. And then dependent on how valuable a certain piece of data is to you, maybe you're willing to evaluate it for, tens of minutes or hours or days of computation to truly know how much data you'd be leaking when you ran a protocol. So our overall takeaways from this, we've provided a method to systematically evaluate leakage using our SAT-based tool. We've expanded a class of approximation problems that we can approach with this maximized SharpSat tooling in our core heuristic. And then we actually also, in the course of doing this work, we generated thousands, actually I think almost tens of thousands of benchmarks of SAT problems, of sharp SAT problems actually, that we've given back to the SAT community, sort of trying to go for some reciprocity in how they helped us out to get their tooling working. Now they can use these to optimize future generations of SAT solvers, which in the history of the SAT community tends to dramatically accelerate the size and complexity of problems which can be tackled in the SAT space. So hopefully those contributions can also sort of pay back dividends in the future and be able to approach even larger problems as we go. And yeah, fun thing. We often run into NP-hard problems and say, well, okay, well we've run that into that, but now we can approach and say, well, if we have an NP oracle, what can we in fact do? So you can check out this work as well as the previous work, Delphinium, in the blue highlighted QR code on the side, and our artifact for this work is available on GitHub as well. Happy to take any questions, and yeah, please check out the full work for the details.
Thank you, Max.